Okay, this is a look at the June 2010 Unit 2 paper. And what I'm going to do is, as usual, look at the way of assessing what the examiner is looking for and how to answer the questions. Alright, let's just dive straight into it. It's a new bit of software I'm using, so if I break everything, well, we'll know why. Let me start off with a little bit of blue. This is an equation of the for the equilibrium reaction between hydrogen iodine and hydrogen iodide is shown below. The curve in the diagram below illustrates the reaction profile for this equilibrium reaction without a catalyst. Right, so let me switch my pen off. Now we've got this little enthalpy diagram. There's a couple of things you kind of notice almost straight away, and one of them, and let's see if this will stay on here, one of the things you notice is the fact that, and you should pick this up, oopsie daisy, I'm drawing on the wrong place, you have a big arrow where enthalpy is pointing upwards. There's a huge arrow here, and basically what that means is the further up, well, the greater the energy. So kind of things to pick up on are the fact that H2 and I2, iodine and hydrogen here, are much higher up, while HI, hydrogen iodide, is lower down. So let's just switch this pen off and see what happens and see if everything disappears. Right, and it does, which isn't too bad because that means we can clear and have a look at the questions. It says, draw on the diagram a curve to illustrate the reaction profile for the equilibrium reaction with a catalyst. And there's 2 marks for this. The reason why you've got 2 marks is as hard or as confusing as it can look. What they're expecting the student to do is, well, have a curve that starts at the reactants and ends at the products. It doesn't really matter where, but I like them to be about the same place. And the other thing they look for is the curve. Whoopsie daisy. The curve doesn't go as high. The curve doesn't go as high. The top end of the curve is here, below the curve, the height of the curve, the original curve. Another way, let's change it to red, would be to draw the same curve, and the classic you may see in your notes is a double curve. And to be honest, let's switch that off and put it back in because it was a horrible diagram. Your curve comes up, you have a double hump, and you come back down to your products there. Okie dokie, that was a little bit better. Oh, that was question 1A1. Let's take the pen off and move forward. Use the diagram to deduce whether the formation of hydrogen iodide, I think red for the typing, hydrogen iodide from hydrogen iodine is exothermic or endothermic. Alright, well, let's have a look. The thing to notice about this again, and going back to what I originally said, is this enthalpy arrow pointing upwards. This set of reactants here, and in my head it's like a system, in that there's this unit of chemicals here, and they've got quite a lot of energy in them, while here they've got less energy. And what I mean by that is in their bonds. So kind of in my head I see them as a number of bonds together, and the hydrogen iodide contains less energy in their bonds, therefore it's more stable. Now if it's more stable, there's an umbrella here, it's more stable, where has that energy gone from the bonds? And we can actually see it here. There's a massive drop, and this energy must go somewhere, and it goes to the surrounding environment. My patterns are getting in the way again. If it goes to the surrounding environment, we will have heat energy given off. So this is an exothermic reaction, giving off heat energy. Okie dokie. Let's switch the pen off. That was a little bit too fast. Just rewind it slightly, stick it on pause. State what the diagram suggests about the sum of the bond enthalpies for the reactant molecules compared with the product molecules. Well, surprisingly and luckily, I've just spoken about that. And what we can say is the sum of the bond enthalpies, the H2 and I2, is going to be, well, let me write that down. So we've got the sum of the bond enthalpies, which colour am I on? Let me go over here. Okay. Not in any colour. Put a pen back in there. Let's go through it. Okay, so the sum of the bond enthalpies of hydrogen and iodine. So the sum of the bond enthalpies, let's get down here. The sum of the bond enthalpies my handwriting's getting neater the more I'm doing this. It's still pretty disgusting. Some of the bond enthalpies for the hydrogen, the iodine, is less than. What should we say? Lower than the sum of the bond enthalpies. Enthalpies of hydrogen iodine. Okay, we'll leave that just there, just for a little bit longer. I think the last one was a little bit too quick. Let's get rid of that. Alright, let's move down to the next question. In terms of P and Q, identify the following for this equilibrium without a catalyst. The value for the activation for the forward reaction. Well, it is equilibrium, so we're looking for the forward reaction in terms of P and Q. I'm going back to the diagram. Okay, what should we do? Back to red, why not? In terms of the diagram here, P and Q are there. And it wants to know the activation energy in terms of P and Q. Well, here, right at the top is the activation energy. And this is where we're starting at. We're starting at our reactant. So P is the actual activation energy. And if we scroll back down to here, so having a quick look at that, we come back down to the question. So forward reaction we've said is P. The second part of the of question 1A4. So here we go, P. The second part of 1A4 says the value for the overall enthalpy change for the forward reaction. So the value for the overall enthalpy change. So that means we want to know how much, and we decided it was exothermic, how much energy was actually given off. So what calculation would I do? So going back up, oopsie daisy, that's the zoom button. So going back up our diagram, we see that if I wanted to work out how much energy was actually given off, I'd take P and I'd take away Q from it. And so you see that gives me a very, very neat calculation, because I'll end up with a negative number. And because it's exothermic, that's the amount of energy I'm going to give off. Okay. So let's switch that off. So the answer to that will be P minus Q. So we'll come back down and over here. Go back in. I'm bored of red. Let's go blue. Let's go. This was P, the activation engine, and the overall is P minus Q. All right, 1B. A mixture of hydrogen and iodine was allowed to reach equilibrium. State the effect of a catalyst on the rate of attainment of this equilibrium. As horrible as it sounds, it's quite a nice one. Because what we know, what a catalyst does, and putting aside what the way they've actually asked it, state the effect of catalyst on the rate of attainment. And I'm not a great one for long words, and that attainment is a long word of this equilibrium. It will increase the rate. It will increase the rate, or speed up the rate of attainment. So what happens when you add a catalyst to a reaction? You speed it up. And that's it. We speeded it up. We haven't altered, and it's not asking us, have we altered the product, the amount of product. It's not, it's had nothing to do with that. Okay. It's a state and explain the effect of an increase in total pressure on the rate attainment of this equilibrium. Well, let's just clear the screen for a moment. And we'll just scroll down. This is a state and explain the effects of an increase in total pressure. Okay, and again, you increase the total pressure, and if we look at, I'm not going to go back up, what we had was hydrogen plus iodine. These were both gases. And it's kind of naughty because you almost want to think, I wonder what's going to happen, which way the equilibrium is going to go, but it's got nothing to do with that question. It asks what is the effect of increasing pressure on the rate. Well, rate will increase. And then we go to a reason of why it will increase. And what you're saying is, and this is what, 2 marker, the 1 marker being over here. And what you're saying here is that you've got more molecules, let's say particles, or particles or molecules in a smaller space, so they're closer together. Smaller volume, and so they're closer together. I do tend to write more than I need to. That's a picture in my head. So they're closer together. And that's your second mark in terms of out of the 3. The final mark, because there are more particles in a small space, because the volume's small and they're closer together, you've suddenly increased. So therefore, I'll put little therefore dots. Therefore, you've increased the chance, the probability of having a successful collision. So that. All right. So we're kind of doing quite well. We've gone through question 1b. So let's switch this back off again. And let's clear this screen annotation software, which I'm kind of enjoying. All right. A student carried out an experiment to study the rates of hydrolysis of some haloalkanes. In the experiment, 2 different haloalkanes were placed in separate test tubes containing silver nitrate solution. Uh-oh, here we go, silver nitrate. The haloalkanes reacted with the water in the silver nitrate solution. The students timed how long it took for the first appearance of the silver halide precipitate in each tube at a constant temperature. This time was used to provide a measure of the initial rate of reaction. The students obtained the following results. Time to form precipitate S. Let's just scroll down. Let's see how much of this we can actually get on screen. Okay, I'm actually going to move it to about here, so we can see let me see the whole question. And it starts off, and before it actually starts off, and before I'm going to actually go down here, I'm going to look at the key words. Silver nitrate clicked me straight away, and as soon as I read it, I went, uh-oh. The reason why I went, uh-oh, is silver nitrate is the most common test. So the only test you'll come across for the halides, for the group 7s at AS in Unit 2. And then it said the word precipitate, so I'm thinking, oh my god, I'm going to come to colours and precipitates. And one thing I really hate doing was remembering and memorising work. Okay. The other thing to realise is the rate of reaction and time to precipitate form, the rate of reaction is faster, like iodobutane, because we're looking at time. So 15 seconds is a lot shorter in time scale than 480. Alright, so all that popped through my head. And I look at state the meaning of the term hydrolysis. Wow. So 1 marker, and it's one of those things where you need to know it. It's the splitting of, I was about to splitting of what? It's the splitting, in this case, the C, the carbon, let's pick one, the carbon-bromine bond. I picked bromine because I felt like it, by the addition of water. So by adding water, by the addition of water, by the addition of water. Okay. And you can see where the mark is. You must say by the addition of water, not just the splitting of the CBr bond, but also by the addition of water. Right, and here comes the memory work, and I knew it was coming. State the code of the precipitate form when iodide ions react with silver nitrate, and write the simplest ionic equation for this reaction. Okay, so silver iodide is a yellow. Oh, let's have some fun. Let's write in yellow. Yellow. I don't know why I'm doing that. Yellow precipitate. Okay. Oh, let's go back to blue. You can barely see that. And the simplest ionic equation for this. And one of the places where a student might make errors is think, oh, I've got silver nitrate, and you know, I've got this carbon bromine bond, and well, I'm looking for iodine, so it's the carbon iodine bond, and oh, what's going to be in the solution? Well, actually, they've highlighted for you the key term, simplest. So what have I got? I've got silver, and you should know it's Ag plus an iodide ion, which is I minus, goes off to form silver iodide, and that I can't get any simpler than that. And believe it or not, that's all they wanted. Okay, now let's see what's coming up next. And that was 2 marks, one for saying yellow precipitate and one for the ionic equation. So we got 2A3. Use your knowledge of the reactions of halide ions with silver nitrate to suggest why the student did not include 1-fluorobutane in this experiment. Okay, let's just write the answer. Because it's soluble. Well, I don't think I'd get 2 marks on that. Okay, right. When I'm talking about it's because silver iodide, silver fluoride, AgF, because we're going to make AgF is formed, and that's 1 mark, and it's soluble, so no precipitate. And you see how I just went and was very blasé about it because it's soluble, and I missed out the fact it was in my head. Silver fluoride is formed, and it is soluble, but therefore there's no precipitate, and I had to include silver fluoride is formed, and it is soluble, and therefore no precipitate. Okie dokie. Let's see, what I might do is just stop there. Go 2B, should we try 2B? The student showed the following enthalpy data to try to account for different initial rates of hydrolysis of haloalkanes used in part A. The student deduced that the rate of hydrolysis of haloalkane is influenced by the strength of the carbon-hydrogen bond in the haloalkane. State how the experimental evidence enabled the student to make this deduction. Alright, well, where are we? Just state how the experiment showed. So these are the bond alphabets given here. So my brain is switched off for a moment. It's to state how the experimental evidence enabled the student to work this one out. Alright, well, what we need to look at is back up at the experimental data. And one thing I did say, looking at this experimental data back here, was that iodobutane formed precipitate very, very quickly. This is exceptionally quickly, 15 seconds compared to bromobutane at 480. So, what we can say is that the bond, and the reason why it formed quickly, it would be that the bond is weaker. If we look at here, there's a carbon iodine, it was 15 seconds. While over here, bond enthalpy for CBr was 480 seconds. Okay. And to write this down, we would say that Ci bond takes less energy to break. As what? It's 238 kilojoules per mole. And therefore, if it's easier to break, the formation of the precipitate will be faster. And will be faster. Okay. Let's switch that up. The student had read that the reaction of water with halocarbons was similar to the reaction of aqueous sodium hydroxide with halocarbons and was an example of a nucleophilic substitution reaction. State the meaning of an electrophile. I'm going insane. This is a nucleophile. Right, a nucleophile would be. Let's move this down. We've finished that question, so let's first move this down so we can see all the two say. A nucleophile is, switch our pen on, an electron pair. Done. I wouldn't just say, it's negatively charged, because the important part is that it donates an electron pair. Okay. When hydroxide ion collides with the molecule of 1-bromobutane, the following reaction occurs. Outline the nucleophilic substitution mechanism for this reaction. Okay, let's have some fun. Alright. Well, when I do this, and as you've seen in the other videos, I kind of like to draw out the structure. I don't draw the hydrogens in. Not quite yet. I don't draw them in on the videos. I do them if it was my exam paper. I've got 1, 2, 3, 4 carbons, 1, 2, 3, 4, is butane in there, and that's what I would do. And I've got this carbon here, and I'm going to attack this carbon, and the reason being, the bromine is electronegative, so it's yanking the electrons towards itself, create a slight positive charge here, and what we're attacking it with is a hydroxide ion, and as I said just prior to that 2C1, it's a lone pair. And what we must do, and we'll very quickly change to red, what we must do is show that this lone pair is going to this carbon atom. If that's the case, all of a sudden we've got 1, 2, 3, 4, 5 bonds on our carbon, and it gives ample opportunity for this bromine atom, whoopsie daisy, where I want this bromine atom to take both electrons and be greedy. So the next step will be to form our final product. And we see, and you can just see in the corner, it's a 2-mark question. What should we do? Should we go for green? Let's go for the green arrow. So what we're going to do is, let's go back to blue. Now we just have to draw in 2, 3, 4. We'll go butadiol. Here's our OH, and just leave it there. And we end up with Br minus. And that's it. And your 2 marks is showing the arrow going from a lone pair. Let's do this in green as well. Here's 1 mark for your lone pair going from your 1 mark from going from your lone pair, a lone pair of electrons from an arrow from lone pair to your carbon, and 1 from your single bond to your bromine molecule. Okie dokie, let's clear that. And let's see how far we are now in question 2. Question 2 is quite long. The reaction of hydroxide ions with 2-bromo-2-methylpropane may occur by a different mechanism from the one in part C. The different involves the formation of carbocation. Complete the following equation by drawing the structure of the carbocation formed when the CBr bond in 2-bromo-2-methylpropane. Okay, so there's a couple of things. The most important thing here is to know well, to be honest, it's almost a given in this question. And they've kind of, let's go back to blue. You've got to know that you form a carbocation, and it's going to form a tertiary. And this mechanism, it's actually quite nice in the way that they've given it to you. The fact that all you're going to have is your positive charge on that carbon atom. Okay, 2D2, state. I would suggest one reason why this reaction occurs by a mechanism involving carbocation, but the reaction part C2 does not. And the real reason being is because this tertiary is a tertiary carbocation. And what should we do? Switch to red. What do you mean by tertiary? Let's go because tertiary carbocation. And what I mean by tertiary is where we see this positive charge here, and I should put around it. You've got on the carbon, that positive charge, you've got 1, 2, 3 other carbons bonded to it with the 3 carbon bonds, the 3 bonds to the central carbon that we've got. Each one is attached not to a hydrogen but to a carbon, stabilising that positive charge. So because tertiary carbocation is more stable. Okay, let's clear that. Let's scroll down. Alright, we're on to number 3. So what I'm going to do is I'm going to stop there. I'm going to stop there and see how the recording went with this new fancy set of software.